Welcome back. So now is the new part of the lecture. It's a switch of material in the sense that now you can take the time to digest what we've seen on validation, data frames, and so on. We will not be using data frames and JSON so much in this lecture, so you can basically consider it a fresh start in something new, and then you can use the exercises of this week in order to fine-tune your knowledge of validation. All right. So this is actually one of my favorite parts of the lecture, because we are actually going to massively process data, in parallel, like billions and billions and billions of tuples or billions of objects or billions of whatever. There is this technology called MapReduce that was invented now. It's probably 16 years ago, I think. That was a revolution in big data, because it's very generic, it's very simple, and it covers a lot of cases. That was the first generation of massive parallel processing. This is why I put a little one here. It's the first generation. Now it would be considered a bit primitive compared to newer generations like Spark, and Spark we will cover later. That's the second generation of technologies. But nevertheless, it's actually quite interesting to look at this first generation of massive parallel processing. Why? Because there's already a lot of things that you can learn about the general principles with which you can query massive amounts of data. All right. The sort of things you can do is actually amazing. This was a picture you probably recognize as the picture of a black hole, right? Where actually you don't see the black hole itself, but you see the halo of emissions around it. This is not actually a photography. It's not like we built a telescope and took the picture and that's it. We have a picture of a black hole. That's not how it was done. The way it was done is that there was plenty of telescopes from all over the Earth that were gathering the photons coming in, the data. And that was actually high performance computing clusters that rebuilt pixel by pixel and computed the way that it looks like. So this is the sort of things you can do with massive parallel processing. So it's actually it's just beautiful. Sadly, we didn't manage to do it with the black hole at the center of our galaxy, the Milky Way. We would have loved to, but it didn't work. This is actually the black hole from another galaxy a bit further away. Right? But maybe one day we'll be able to do it for Sagittarius A star in our galaxy. All right, anyway, that was just a parenthesis that I wanted to make to show you the sort of things that we can actually do. This is our stack. You know, always the same one that I'm showing almost every week. And now you see we've already done almost half of it. We are halfway through the lecture, and now we are going to the processing level. And then we continue to work our way up that stack. All right. And we are going to start with some field experiments with a concrete use case. I think it's the best way to understand MapReduce, to actually look at that example. So in the last weekend, I went for a Pokemon hunt, and I managed to catch a lot of Pokemons. But the thing is, I would like to count them, and there's a lot of them. I actually, in that case, I have 400 plus. It could even be billions of them, right? But all I know is that there are 10 different kinds of Pokemons. I actually don't know all the names. I just know that this one is Pikachu. It's probably the most famous one, so that I know. I don't know the names of the others, but these are the 10 forms of Pokemon. And maybe I have several of the same form. And I would like to count how many of each. So of course, you could imagine I could just put them all on a table, sit at the table and sort them and then count and so on. But maybe that wouldn't be efficient. And it turns out that there are more efficient ways to do that. And the idea is that some years when we are ahead of time, we can even do it in class, but now we don't have we are not in front of the schedule. So this is why I'm just explaining on the slides. The idea is that you can distribute these Pokemons. You can shard them. Guess what? Shards, blocks, chunks, splits. You know, I told them there's many names. So we are sharding this collection of Pokemons, and we are just distributing these shards to different volunteers. So this is just a partition of my Pokemons. Every person that is a volunteer for that first phase has a subset of the Pokemons: one shard, one chunk, one block, one split, one partition, whatever you call it, right? Let's call it a shard. So this is a shard here, and this person is going to just count in the shard that they got, the number of each, right? So here we see we have 2 Pikachus in there. You see 1 and 2 Pikachus, and then we do it all for the others, right? So this is the first phase. It's actually called mapping because we map this shard to this structure. It's actually a key value model, right? The keys are the Pokemons and the values are the numbers. All right. This is task 1. It's actually called mapping. Then there is task 2. What's going to happen is that some people are assigned specific Pokemon. So for example, this person is responsible for Pikachu. What's going to happen is that she will receive all the key values. So this would have been to be cut, right? We just separate these key values like that. And then we just shuffle around by distributing these keys so that all the Pikachus in the room from all the various people who are responsible for the shards in the first part, just distribute their Pikachus to this person. And then what this person do, it's called the reducer, the reducing phase. All the Pikachus then get added, 1 + 2, 3, + 1, 4, + 3, 7, + 1, 8. There you go, 8. So there's 8 Pikachus, and that's the total in there. That's the output of the reducer. So now we have 8. And then at the end, you see 8 Pikachus, and there's the other volunteers that took care of the other Pokemons. And this is the output that we have. And it turns out that if you have a lot of Pokemons, this is much faster than me alone doing it on my table, counting the Pokemons one by one. So what happened in there? 2 things. The first thing is that it's the parallelism. It's the fact that there were 10 different people processing each one shard of it. The same goes for the second phase. Each had a Pokemon, and this was all done in parallel. Parallelism. The second thing that is happening in there, it's batch processing. Why? Because the mappers here have batches. This could be called a batch, a shard. So it's a batch of data that is processed at the same time, right? This is basically in a batch, single batch. You have all these Pokemons and you count them. So you see that it's parallelism and batch processing. Right? Batch processing is not something new. We've seen it in HBase, remember, when we had this data written as sorted key value pairs on disk, right, with HBase. Well, this was already batch processing. So now it's again batch processing and parallelism. Okay. It turns out that what we've just done is a MapReduce job. Right. So if you understood what went on with the Pokemon, you basically know MapReduce. And everything that's following is just now the theory and the formalism behind it. But okay, who understood what went on with the Pokemons? Just checking. Can you raise your hand?
Yeah, I see a few hands.
Okay, that's great. Then you understand MapReduce. Right. Okay, then the rest will be a walk in the park. Okay, so far we have our storage as a file system, HDFS. HDFS can have text files, right? Maybe you threw a lot of text, billions of lines. It can have CSV files. Maybe we have CSV files with billions and billions of CSV lines that are each rows in a table. We can have plenty of raw files. So you see all the formats you can have in HDFS, right? You can have now billions of lines. You recognize probably here some sort of dates. Here you probably recognize contents. Maybe you can have key values, right? Maybe I have space separated on every line. I have a year, and then I have some value in there. Maybe I have JSON. So I'm going to have billion of JSON lines with the year, the dates, the duration. Did anybody recognize what this is, by the way? Every year, somewhere in April, the duration, content. Anybody sees that? That's Arciluter, right? That's the Zechioloiten festival. So these are all the durations here stored in there in that format. But anyway, it's just an example. So what I want to show you here is just that there's many, many formats that you could have in there. So I'm just focusing on text, but of course we saw that there can be other formats in the previous lecture, right? It could be binary. Maybe this is a huge Parquet file, right, that I've stored in there, so it's just zeros or ones. There's even some specific formats specific to Hadoop, but they store generic key values, you know, a bit like HBase, actually. We've seen key values in HBase, so maybe we also have that sort of things in HDFS. All right, and now we want to process it, obviously using MapReduce, right? This is a MapReduce lecture now. Now, one more thing about the way it's stored in HDFS or in S3. What is very, very common is that instead of having one single big file, we usually have plenty of files. We have part 1, part 2, part 3. These are kind of already batches in a way. So it's very common that when you have a data set in HDFS or S3, it's actually divided in parts, right? That are all indexed with some number. And usually these parts are within the same directory. It will become obvious later why this is the case. So anyway, we have storage as the file system. We can store stuff. We even have, if we want to not store directly ourselves the data, we can use HBase. We saw that HBase is taken care of it, of storing big tables on HDFS, and then we only need to deal with the table, right? So indeed, we could also have tables if we use HDFS, and maybe we have billions of rows, right? Maybe I use XML. Maybe with HBase, that's the best way actually to store XML. You basically store one XML document on every row of HBase. That's one way of doing that. And maybe you have a schema right there that all the objects there satisfy. But anyway, these are many ways to do that. But every time I have billions of whatever, billions of objects, billions of lines, billions of rows, billions of stuff. And these billions of stuff is something I want to query. And in order to query it, we are going to use the magic of the clusters, because now we have thousands of machines at our disposal in our data center, and we are going to just shard the data, and we are going to do all of that in parallel. This is what we are going to discover right now. So this is the, actually, you probably saw that a few years ago, but basically this is what we do in the data, right? We could call this work of our data is in the shards, right? Okay, so let's start, as I said, with this first generation of massive parallel and batch processing. Let's zoom out. What do we want to do? Well, we have some input data. We want to query it, and we want to get output data. Moreover, we want to do it in parallel, meaning that we split here the input data into shards, and we probably want to process one shard at a time in batches. Okay, so what's the ideal and simplest case that could happen if we are lucky? The ideal case would be that we just take one shard, execute the query on just one machine here, and output that shard. Then on a second machine, you look at this other shard, execute it, create this output shard. That would be beautiful, right? That would be easy, actually, if it worked that way. Well, in some cases, it actually works that way. But the problem is that in many cases, it doesn't. In many cases, it's a huge spaghetti thing, because in order to compute the data right there, you might need data from all over the place. This is a huge spaghetti dish in the middle, and of course, it doesn't work that way. So this is reality, basically. You actually need to solve a challenge here in order to make it all work, because of all the way that this is all entangled in the computation. But in a typical case, it's actually not a spaghetti like that. In a typical case, it's a bit messy, right, in the way that the computations happen, but nevertheless, there is a bit of order. And in particular, if you look at what's going on in the computations we want to do, at some places, these are things you can do in parallel very nicely, if you look at some places, and at some other places, there is spaghetti, right? So at some places in parallel, some other places, spaghetti. So there is a bit of structure in the mess, so to say. So we have map here, that's what we call mapping actually, and what we call shuffle. Shuffle is a word I'm going to say a lot. Right. So it's based on this premise that MapReduce was actually invented. So how does MapReduce work? It's a way, a computing paradigm, if you want, a platform in order to execute queries that have the structure behind me. What structure? Well, we first have something that goes in parallel. Then we have a big shuffling with the spaghetti happening. So this is where the data is flying all over the cluster. It's a huge mess, actually. It takes a lot of time. So we shuffle around. And then we have a second part that, again, happens in parallel on the machine. And then we output the data. This here, if you want just one picture, this is MapReduce. Map, reduce, and we have the shuffling in the middle. And actually, it should be called Map Shuffle Reduce. I don't know why it's not called Map Shuffle Reduce, because the shuffling part is really, really, really annoying, because this is the part where you have the big mess with the data flying around. But anyway, map, reduce. And it's super simple, extremely simple. It's extremely powerful, and a lot of problems, a lot of data analytics can actually be done with this very, very simple high-level view of the query. Do we have a question?
Is the data already reduced in some sense before shuffling?
We look into that. It's called combining. So you can indeed pre-reduce the data in order to diminish the quantity of data that gets shuffled. You're already asking an advanced question, right? This is something we'll study at the end of this section, probably next week, that indeed you can pre-reduce some of the data there and have less shuffling in there, and then you alleviate a bit the last part there. That's already an optimization, very smart. Right, any other questions? No? All right, no. So let's just go into more details. So obviously I need to give a name to whatever is in there. So let's call it intermediate data, right? So the intermediate data is whatever gets shuffled around. It's basically the output of the map phase and the input of the reduce phase. You're welcome. Okay, well, one more thing. In MapReduce, everything is a key value pair. It's exactly, you know, there's this saying, when you have a hammer, you see the world as a nail. Well, MapReduce has a hammer from key value pairs. So it sees everything as a key value pair. So for MapReduce, no matter what you process, it's going to be collections of key value pairs. Right? All right, so we have key value pairs in the input, key value pairs in the intermediate values, and key value pairs in the output. Right? And if it's not a key value pair, we just hit it with a hammer until it is a key value pair. Right? We just need things to be key value pairs. All right. Now we might have types. What are the keys? Maybe they are strings, maybe they are integers. I don't know, but they have a certain type, right? So there's a key type here and a value type. In the intermediate data, maybe it's a different sort of key and a different sort of value. And maybe in the output, it's yet another form of key and yet another form of value, right? So I'm using different forms of writing in there. Very often, though, the types of the keys in the intermediate values and values are the same as in the output. This is actually why we can, as you asked the question earlier, pre-reduce things already a bit in there. But it only works if we have the same types here and there. Okay, so I know I've already done it with the Pokemons, but let's do it without Pokemons now to make sure that you also have it on an abstract perspective, even if you don't have the Pokemons anymore. So what's happening? So now, you know, I'm not saying Pokemons anymore, I'm saying key, right? And I'm not saying count number of Pokemons, but I'm saying value, but basically the keys are the Pokemons and the values are the numbers, right? So from a formal perspective, we have billions of key values that are input collection. I told you everything is a key value, right? So we have billions of key values in the input. The first thing we do is we shard it, we split it, we chunk it, we partition it, whatever you call it, we split it, yeah. I use split right there. I think MapReduce calls it split, actually. That's why it says split. But we cut it into pieces and we have the splits. So now I have 3 splits. In practice, you may have thousands of them, but let's do it 3. Second, you map. So this is some function that you as the user are providing, right? A mapping function that tells me programmatically, and you actually tell me that, how out of this one input key value, I produce one or several, or maybe 0, intermediate key values. This is given by you, the user, right? So this is from the perspective of MapReduce, it's a black box, it's open, and it's user provided. You do it in parallel, applying this map function on all the key values, shard by shard, and then you get these intermediate key values, just applying the map function. Next, logically, it's not something that actually is physical because you wouldn't fit petabytes on the machine, but logically, you mentally in your mind put all of these intermediate results together, sorted by key. So now it's all nicely sorted by key. And now you see that they are already grouped. If you sort, then you group also. So you have key 1 together, key 2 together, key 3 together. So now you partition it again, but this time, you know, by key. So now you have a group here with key 1, a group with key 2, a group with key 3. Then what happens is that you take all of the key values that have an intermediate key 1, you use the reduce function, also provided by you, the user, and get 0, 1, or more output key values. Then you do it for, so typically it's going to be actually the same type here and there, and it's going to be a sum or an average or whatever of these, right? Okay, it can actually be more than 1, but very often it's just 1. is output by reduce. Now, the same as for map, you do it in parallel. So you call the reduce function on all of these groups from the intermediate values and get that. And that's it. So now I redrew everything that I've shown you, right? You have the input collection of key value pairs. You apply the map function in parallel to get these intermediate values. This is now the shuffling. So you logically, it's as if you would sort them and then split them again, but now you have the same key in every group right there. And then you apply the reduce function to every group that has the same key and get the output. This is MapReduce. I've just explained the second time what I've already explained to you with Pokemons, but this is basically always that same way with the mapping phase and the reducing phase that goes in parallel and batch processing. Everything clear? Any questions so far? All right, no questions. Well, I think, okay, let me stop here, right? It's already 11:53. Let me stop here. I think you've had enough for today, right? So take a picture of that. This is MapReduce, or take the picture of the Pokemon if you prefer, if it's easier to understand, but this is pretty much it. So next week, I'll just explain to you how this is all implemented, right? Because that's the logical aspect. But now you're probably wondering, how do we actually do that on the cluster of machines? So this I will explain to you next week, right? So thank you very much for following today's lecture. You have even a few 2 minutes, extra minutes to go to the Mensa and enjoy your lunch. If you have any questions, please ask them on Mattermost. We are here to help. The TA team is working on exercises, so you'll have exercises on JSON schema, JSON, XML schema. I encourage you to do it. Please download Oxygen from the IT shop if you haven't done so, because Oxygen will also allow you to validate with JSON schema and XML schema. For validating with JSON, I will give you a link to some page where you can also validate with JSON, right? Okay, so that's it for today. Thank you very much, everybody. Thank you, Wenxi, for moderating the lecture. Enjoy the exercises this week. And as for me, I will see you next week for the continuation of the course. Thank you and goodbye.